My day is going fine. A little bit nervous because this is the first time I'm teaching this this way. I'm not as keen about remote learning as I am about in-person learning. I don't watch much anime, no. Good morning. So there's approximately a 3-second delay between the time I speak and at least the time I see myself speaking on this tablet. I'm guessing it's about the same for you guys. So so there'll be lots of pausing while when I ask for feedback. I'll wait a few seconds, and there'll be a silence that feels awkward, at least for me. Am I a gamer? Not really. I don't have a lot of time for games anymore. Job and children kind of soak up all that time. So you asked if the lecture is going to be recorded. Yes, this YouTube broadcast is being recorded, but more importantly than that, there's another entirely separate camera recording everything that's happening, and I think it's going to be a slightly better quality, so I will upload that video within 24 hours. How hard is this course? That varies depending on the students and how much effort they're willing to put in. For some people, it's not a difficult course at all. I would like to keep it at the very least sort of approachable, so people don't get discouraged. All right, so now we've reached the actual start time. So I'll go over the course outline and then give you a sort of a teaser lecture today that covers some of the topics we're going to discuss. So let's remember that getting responses from you. So I do encourage you, someone mentioned creating a Discord. If you want to do chatting outside of on a sideband, that's fine, but please don't clog up the YouTube chat with huge discussions, because then I won't actually be able to see any questions that come up. So first off, this is me, Pat Morin. I'm a professor at Carleton. I've been a professor for a very long time. If you need to call me, you can just call me by my first name, Pat. I don't need any title or anything. And if you don't feel comfortable doing that, then you can just avoid calling me by name at all. So you can just ask your question. It's really easy now since we're in this remote learning setup. Either we'll be doing a Zoom chat, in which case you'll be right in front of me. You don't have to call me by name, or you're just chatting over YouTube, in which case you also don't need to call me by name. The course is COMP2804. Here's the web page for the course. I assume that you've found that already, because that's really the only way to find the YouTube lecture if you're here. Almost everything we do will be available on this web page, so all the assignments will be there. You'll see that the textbook is there. Sample solutions for the assignments will go there. Sample exams and so on. The only thing that we'll be using CU Learn for is submitting assignments, and probably when it's time to do midterm and final exams, those will somehow be integrated into CU Learn. We'll cross that bridge when we come to it. Unlike some other courses, the grading scheme has not changed in the online format for this course. So there will be 4 assignments worth a total of 25%. There'll be a midterm exam also worth 25%, and a final exam worth 50%. So that feels like a lot of weight on exams, and it is, but you'll be well prepared for them. You'll have lots of sample questions from previous year's exams to study from and to practice on. So it's people don't seem to struggle in preparing for the exams for this course. Put in the work, you will definitely be able to do questions, practice questions that are very similar to questions you'll find on the exam. And the textbook for this course is written by the instructor of the other section, Michiel Smid. It's called Discrete Structures for Computer Science, and it's available on the course webpage as a PDF. It's a very good textbook, very well written, both precise and concise, and full of interesting examples. So I highly recommend it. And pretty much every topic we do will be from that textbook, with a couple of exceptions. And for those exceptions, notes will be provided for the course. So I will check if there are any questions. Okay. So it looks like there's no questions right now. Before I start with the sort of teaser material, the teaser topic for this course, introduction to some of the things we'll be doing. Now is the time. I'll give you 20 seconds to ask a question that you want. Yes, there is no coding in this course. This is really a course about reasoning about discrete structures, meaning it's a discrete math course. So they're really math assignments. There are no tutorials for this class. These tutorials mostly end after first year, but we will have tons and tons of office hours. So we have, between the two sections of this course, we have something like 12 TAs. And last time I checked, we basically had people holding office hours every morning and every afternoon of every weekday, Monday to Friday. So there'll always be someone to consult and ask for help. And some of those office hours sometimes devolve into mini tutorial sections or mini lectures delivered by the TAs. How similar will these lectures be to the ones already on the website? Quite similar. We'll be following most of the same topics. I think we might swap out one or two topics because we have some new material that's sort of relevant to the current situation today. Material on group testing, which is related to pool testing for virus testing, so efficient testing. But mostly the list of lectures that you see there, the list of videos that you see there will be I'll be doing almost the same material. Yes. Someone asks, should we refamiliarize ourselves with the content of 1805? The answer is yes. We will be using basic concepts from discrete math. So we'll be talking about things like graphs. We'll be doing proofs by induction sometimes, and general logic and proof strategies. So direct proofs by contradiction. We'll be doing those things. Whether or not that means you have to go back and review everything, or whether you should just review it as it comes along. If you're struggling with something, ask me. I can usually have time to do a quick review of these things while I'm teaching. So don't go back and redo the whole course, 1805. But yes, that's the most relevant material for this course. Yes, all live videos will be uploaded. I mentioned this a little bit earlier. This, by default, YouTube will keep this video, make this video viewable after I end the stream. But there's also a video camera in this room recording this, which gives a slightly better picture of the board. I believe it's kind of blurry in the corners here. That's an artifact of a webcam. And so there'll be a slightly better quality lecture as well. The other thing that I should mention is if something goes desperately wrong with the live stream, I lose an internet connection or whatever, the sound stops working, power goes out, whatever. I plan on just continuing the lecture basically to an empty room by myself, and then the version of it recorded by the video camera will be posted. Are all the tests open book? Not traditionally, no. We're going to have to figure out exactly how we're going to deal with the fact that tests will be online. So we'll see. But in general, the open bookness or not of tests makes no real difference. If you're familiar with the material, then you can answer the questions on the test using the knowledge that you have. And if you're unfamiliar with it, then having online resources won't really help unless those online resources include somebody who knows the material to do the test for you. And we like to avoid that. There's no double pass rule or any pass rule for this course. Your grade is based on this grading scheme. Whatever that adds up to at the end is the grade that you get. Is having a webcam necessary for the midterm? I think if you don't have a webcam these days, then you're going to struggle with a lot of things. In particular, I'm aware of a number of courses, and in fact, the e-proctoring system that Carleton is using these days can require that you have a webcam on in order to write an exam. And so if you don't have a webcam, I suggest you get one. They're cheap compared to everything else. In particular, the one I have here is less than the cost of many textbooks. And so since you don't have to buy a textbook for this course, you can spend that on a webcam. Yes. This 50% final exam mark is worrisome for a lot of people. I understand that there are people who stress about exams. That's why we try to make it as stress-free as possible by preparing you as much as possible. So the last count, I think we had something like 300 sample exam questions for people to prepare and study with, of the exact same format that appear on exams, multiple choice sort of math questions. And so if you're the kind of person who gets really anxious about these things, well, you can take that away by really working through all of those questions. And if there's some of them you can't do, you have plenty of time to get help or discuss with friends. So the final exam with 50% is certainly a lot, but I hope that by the time we get there, you'll feel confident and ready for it. Okay, so there's some questions about the logistics of exams, screen sharing, and how we're going to catch cheaters and so on. I don't know yet. Carleton seems to be developing system for e-proctoring and is offering help with it. For now, we picture something like you write an exam which is perhaps different for every single student. The nice thing about having a large bank of possible questions is we can actually give every student a different exam. So you can't just copy off a friend. And we can ask you, there's some sort of rules outlined there about what this exam will look like, but you'll have a camera on, and at some point you'll sign in. We'll check in with you, and at some point before you leave, we'll sign out. But let's not get ahead of ourselves there. Yes, office hours for TAs are currently being scheduled now. Initially, I was going to do office hours over Zoom, but that becomes a bit of a problem because of the class size and because the number of people who don't have Zoom licenses. So it may happen over a big blue button instead. Office hours will begin next week, and information about exactly how to attend them will be available on the webpage. Big blue button, if you haven't heard of it, is something that Carleton pays for, and it's integrated into C2Learn. Okay, so I'm going to start on some actual course material. And today is, as I said, it's a bit of a teaser lecture, meaning that I will show you some of the things types of things we'll be learning about in this course. And we'll do a proof or two, but sometimes we'll just see the kinds of problems that we're going to look at and maybe the statements of the results. And later in the course, we'll get to actually being able to prove those things. But first, let's start with a ill-posed or ill-stated theorem. I'll call it a pseudo theorem. And it says the following: among any group of 6 people, there are 3 mutual friends or 3 mutual strangers. Okay, so the first thing that you should say and wonder about is, well, what do these words mean? What does it mean for 2 people to be a friend? What does it mean for 2 people to be strangers? So I say that this is a pseudo theorem because there's some things in here that are not defined, and the definition of friend or definition of strangers that you could maybe consider is, you can say that 2 people are friends with each other if they have ever shook hands. So expect not to make any friends for the next year or 2 under that definition. So if 2 people shook hands, then they're friends with each other. So that's a symmetric relationship. So if I shook your hand, then you shook my hand. Another way to say that is P is a friend of Q if and only if Q is a friend of P. And if that's never happened, if these two individuals have never shaken hands, then shook hands, then they're not friends, they're strangers. So there's nothing in between. There's no shades of gray. 2 people are either friends or they're strangers. I believe that the Facebook friend graph works like this. So friend, being someone's Facebook friend, is a mutual thing. Someone has to ask, someone has to accept. After that, both of those people are friends. And if that little transaction didn't happen, then they're not friends. So we'll call them strangers. So just to be clear, the assumptions are, for any two people, P and Q, two different people, exactly one of these is true. P and Q are friends, or P and Q are strangers. They can't be both at the same time, and they have to be exactly one or the other. So, questions about the setup? So it's clear what we're talking about here. So I say the claim is if I put any 6 people into a room, then I can pick a group of 3 of them where all 3 of those people know each other, they're friends, or all 3 of those people don't know each other, they're strangers. So I can basically take half the people in the room in this case, if the number of people is 6, and they're either all friends, you sometimes call that a clique, or they're all strangers, you sometimes call that an independent set. Okay, so those words clique and independent set, they come from, they're used in graph theory, although clique is a much older term that actually makes sense when you're talking about friends. A group of people, all of whom are friends, tend to be a clique. So since we seem to be talking about something related to that fits into the notion of graph theory, let's think about this in terms of a graph and maybe state a similar thing. So we have 6 people. And think of those as the vertices of a graph. And this friendship relationship is between pairs of people. And similarly, the stranger relationship is between pairs of people. So that suggests that the edges of the graph can be used to model this. And indeed, what we'll look at is a graph that has 6 vertices, and every possible edge is in there. So if I take any 2 people, I can either say that those 2 people are friends, in which case I'll draw a red edge between them. Red is a nice warm color for friendship. Or those 2 people, maybe they're not friends, so they're strangers, in which case I'll put a blue edge between them. Okay. So for example, this person here, let's say you want to call this person V. Among the 5 other people in the graph, they are strangers with 2 of them, and they're friends with the other 2. Okay, and for every pair of people, there's an edge between them, and that edge has some color. So we'd have to finish this thing. Maybe this is a really lonely person. They have no friends in this group. Maybe those 2 are strangers. And four, 5, 1, 2, 3, 4. 5, 1, 2, 3, 4, 5. Okay, so that's the picture. Graph with 6 vertices. Every edge is in the graph, and every edge is either red or blue. And what is the theorem planning? Well, it's claiming that we can either find three mutual friends in this graph version corresponds to some group like this, in which those three vertices form a cycle of three, consisting of three red edges. So they're a red triangle in the graph. Or we can find three people who are mutual strangers, and we have an example of that in this graph, which is this vertex, and this vertex. The three edges between those three people are all blue, meaning that they're all strangers. So theorem doesn't say that it's exactly one or the other. In fact, and here's an example where both things happen, but at least one of them has to happen. And certainly it can be the case that one of them doesn't happen, because there's nothing that stops me from making a graph where all the edges are red, in which case I can't find a blue cycle, a blue triangle, or making a graph where all the edges are blue, in which case I won't be able to find a red triangle. But you'll be able to find at least one of those two things. Okay. It's clear, the statement of this? All right. So this is a statement about any graph on 6 vertices. Let's write it down precisely. And we'll say something like, now it's a real theorem. Let G be a complete graph on 6 vertices whose edges are colored red and blue. Then G contains a monochromatic 3-cycle. Monochromatic just means all edges of the same color. 3-cycle, this just means a cycle of length 3. So any 3 vertices give you a cycle of length 3. They're the triangles we've been talking about in this picture. Okay. So either all the edges of the cycle are red, or all the edges of the cycle are blue. Okay, so someone asks, what if we make the majority red or blue? So for instance, what if all the edges are red? Well, then this is still true, because I take any 3 vertices, and the cycle that joins them is red. So it's a monochromatic 3-cycle, just like the theorem guarantees. Same thing if I make all the edges blue, take any 3 vertices. The cycle that joins them is blue, so that also satisfies the theorem. So let's try to prove this thing. And we'll work through a proof by reasoning about the graph, but not drawing the whole thing first. Instead, we'll just draw the vertices, 1, 2, 3, 4, 5, 6. So now we're actually going to try and prove this thing. And I'm used to teaching on something like a 24-foot chalkboard. Sometimes the chalkboards even go up and down. So I'm going to try and cram things onto this these little whiteboards that I have here. They're only about 8 feet, 8 feet across. So things may get a little bit cramped, but actually that happens even when I have chalkboards, big ones, because I'm not great at managing the space. I'll have to be a little bit more careful today. So, so to start the proof, just take any vertex V. So let's just pick one arbitrarily. There's our vertex V. Now, V has edges leading out of it to the 5 other members of this group, or the 5 other vertices in this graph. So V has 5 incident edges, each colored red or blue. And I can write this as a little equation that says red plus blue is equal to 5. R plus B is equal to 5. R is the number of red edges incident to V, and B is the number of blue edges incident to V, and the total number of edges incident to V is 5, so together those two numbers add up to 5. So maybe the picture looks like this. 1, 2, 3 red, and 1, 2 blue, and indeed that does add up to 5. Okay, is that clear? All right. So, what can we deduce from this? Well, I claim that at least one of these two things is true. Red is bigger than 2. The number of red edges is bigger than 2. Or the number of blue edges is bigger than 2. These are the edges incident to V. So either that is confusing to you or it's completely obvious, but basically saying that, well, the number of edges adds up to 5, and there's 2 kinds of edges, red ones and blue ones. So somehow the average is 2.5, which is bigger than 2. So both these numbers can't be less than or equal to 2. Another way to think of that is you can just do a very quick proof by contradiction. If red is less than or equal to 2 and blue is less than or equal to 2, then red plus blue is less than or equal to 2 plus 2 is equal to 4, but that's not equal to 5, and I know that red plus blue is supposed to be equal to 5. Okay? So there's a very short proof by contradiction. This idea we will come back to later in the course. This idea of saying, well, when I take edges or objects and classify them into 2 classes or even more classes, then somehow one of them is bigger than or equal to the average. That's called the pigeonhole principle. And we'll have at least one whole lecture devoted to cool things that you can prove with that later in the course. But for now, I think you can convince yourself that there's either at least 3 red edges or at least 3 blue edges. Okay. So I'm going to say something that you'll see frequently without loss of generality, assume that the number of red edges is bigger than 2. Okay. What does this without loss of generality mean? It's a way of saying that the things that we're talking about here are completely symmetric. So red edges and blue edges, they both play the same role in the statement of the theorem. And I know that one of those two is bigger than 2. And so let's just assume that it's the red edges, because everything that we're going to say after this, we could just interchange the roles of red and blue, and everything that we say would still be true. Okay? If you don't like this, then you can say, you can break it down into cases and say, case 1 is if the number of red edges is bigger than or equal to 2. Case 2 is if the number of blue edges is bigger than 2. And if you do that, then what you'll find is once you do case 1, case 2 is you repeating everything but changing the roles of red and blue. Okay. So we're assuming the number of red edges is bigger than 2. Just like in the picture here, the number of red edges is 3. That's bigger than 2. And we know that since the number of red edges is an integer, if it's bigger than 2, that means that it's bigger than or equal to 3. Right? It's strictly bigger than 2, therefore it's bigger than or equal to 3. Okay. And now we're almost done. We'll say let x, y, and z be edges, or not edges, vertices such that Vx, Vy, and Vz, these are edges, are red. So in this picture, here is x, here is y, and here is z. Okay? So, now we have 2 cases to consider. What are those cases? One of them is that x, y, z has 3 blue edges. So I look at this triangle formed by x, y, and z. Those are 3 edges that are not in my picture yet. And one possibility is that all 3 of those edges are blue. Okay. If that happens, great, because I have just found a triangle, a 3-cycle, x, y, z, all of whose 3 edges are blue. So that's the easy case. Otherwise, so that's case 1. And what's case 2? Case 2 is at least, if they're not all blue, one of x, y, y, z, or z, x is red. So it's not this case where they're all blue. Instead, one of them is red. At least one of them is red. So maybe it's XY. In fact, again, you can use this phrase, without loss of generality, xy is red, because it's one of those three, xy, yz, or zx, but it doesn't matter which one. We're about to finish, we finish the argument the same way. So without loss of generality, we'll say xy is red, okay? But now we're also done, because vxy is a red cycle. Right? Remember, V, we looked to see that it had more red edges than blue edges. And then we picked the endpoints of those edges, X, Y, and Z, to be endpoints of red edges. So all those edges incident to V, in particular the edge Vx is red. That's the way we chose it. That's the way we chose X. The edge Vy is red. That's the way we chose Y. And now the edge xy is red, so Vxy is a red cycle. Okay. And that's the end of the proof. Not a difficult one, but a pretty one, and not. It's hard enough that you don't just see the statement of the theorem and immediately understand why it's true. You have to do a little bit of reasoning, and it illustrates some nice examples. In particular, it uses the pigeonhole principle, which we'll look at later. There's a little proof by contradiction, and just a nice little case analysis. So, any questions about that? Okay, so if you're a mathematician and you see something like that, a pseudo theorem, a theorem like that, and a nice proof like that, you immediately start to ask yourself, well, what about bigger numbers? So this theorem talks about a group of 6 people. What if I have a larger group? What if I have a group of 8 people, or 10 people, or 1,000 people? And if you like to pick patterns, what we saw was that 6 people, that guarantees clique, that's a group of friends, or independent set, that's a group of strangers of size 3. And you might think, oh, well, what if I have n people for some large value of n? Does that guarantee a clique or independent set of size, well, n over 2 looks like a nice answer, right? 6 goes to 3, so n goes to 1/2 of n. Looks like that might be a reasonable guess. So what do people think? Is this true? So probably not with a question mark. N over 2 seems way too big. No, I don't think so. Seems too easy to be the answer. Yes, so you are correct. It's not true in general. And one of the things that we will see in this this course is it's not even close to n over 2 that you can guarantee here. In fact, there's some nice constructions, in fact, probabilistic constructions that show that it's much smaller than that. It's more like log n. And I won't tell you the details, but that result says that, well, you can take 1,000 people and in that group of 1,000 people, you can't find any clique or independent set of size 20. Okay. So not even close to n over 2. So it's actually more like 2 times the logarithm of n. But that's for another day later in the course, once we've learned some probability, and this will be a nice example of a way to prove that certain things exist without actually finding them. Just arguing that if you do some randomized thing, then that thing seems to show up, okay? Even though maybe you can't explicitly find that thing. Okay. So that's example number 1. This is an example of what's called Ramsey Theory. And Ramsey Theory studies these questions of, if you give me something large, typically a large complete graph with some colors on the edges, that something is guaranteed to show up in that picture. In this case, it's a large clique or a large independent set, but not incredibly large, just getting, the number of vertices in the graph. Okay, so next thing to look at is something you may have heard of before. It's a sorting algorithm, and it goes by the name of quicksort. It's a very old one, goes back to the 60s, and it's one that's used a lot. It's very easy to implement, and it has some nice properties. In particular, you can implement it, if you're careful, by if you have an array of elements to sort, you can do the whole thing entirely in the original array. You don't have to allocate an extra array to hold the data, the sorted version. You can do it just by moving things around inside the original array, which is useful when space is at a premium. And it's easy to describe if I don't want to bother about all the details of how you move things around inside the array. So what you have is you want to sort an array, and I'll call it A1, up to AN. I know that almost no modern programming language uses array indices starting at 1, but it's nice to not have to write n-1 everywhere. So I'll just do that. And here's the way quicksort works. If n is less than or equal to 1, well, that means you have an array whose length is either 0, in which case there's really nothing to do, or its length is 1, in which case I guess it's already sorted, right? So sorting is a relationship between pairs of things that says if I is less than j, then the array element at position I should be less than the array element at position j. But if there's only one element, then you have no pairs, so it definitely satisfies the definition of sorted. So if n is less than or equal to 1, then do nothing. Or if you like, just return the original array. Let's call this thing A. Otherwise, compare everything to A1. So you take the first element of the array, A1, and that partitions into something that looks like this. So if I compare everything to A1, well, it's either smaller than A1, or it's equal to A1, or it's bigger than A1. So we'll use that to partition into 3 parts. In general, there's one element in the middle that's equal to A1. And then there's some part X, which is all stuff that is smaller than A1. And there's another part Y, which is the stuff that's bigger than A1. Okay? And that's clear. It's clear that it's enough to take A1 and compare it to the n-1 other elements in the array to figure out which things go in X and which things go in Y. Okay? So we'll make note of that and say that that requires n-1 comparisons. Okay. Now here's the cool part. So you partition this way, and if the fun exercise is to try and do this in the same array that you started with, so that's possible, but we won't do it. It's just a little bit of careful thinking about where things should go after they're compared with A1. Well, then all that's left to do is recursively sort X, and then recursively sort Y. After I recursively sort X, well, this part of the array is sorted, and everything in here is smaller than A1. And after I recursively sort Y, this part of the array is sorted, and everything in here is bigger than A1. So in fact, the whole array is sorted at that point. Okay. And indeed, if you don't care about doing this in place, quicksort is 3 lines of Python code. If you like list comprehensions in Python, you can basically do this. There's the if statement with the return, and then one list comprehension does the rest. So very, very simple algorithm. And you can ask, how fast is quicksort? Now, presumably, it wouldn't be called quicksort if it were slow, but that could just be advertising hype. So we'd better, as computer scientists, we'd better check this. So just because someone calls their algorithm the fast algorithm, the quick algorithm, or even the optimal algorithm, names don't always tell you everything about this. So let's think about an example. I have this big array, A has A1 up to AN. And now I take A1, so maybe let's I take A1 and I compare it to everything else in the array. So maybe this is the way A started. I compare it to everything else in the array, and I partition into those three parts: the stuff less than A1, the stuff equal to A1, the stuff bigger than A1. Well, if this is my input array, it contains 1, 3, 5, 7 to, let's make them all distinct, 4 in this order. Then this is A1, this is A2, A3, A4, A5, A6. Then after I do this partitioning, well, A1 is the smallest element in the array. So once I've done this, A1 is still going to be the first thing in the array. There's nothing in X because there's nothing smaller than A1. Everything goes over here in Y because everything is bigger than A1. So X is empty here, and this is Y, and Y will contain 3, 5, 7, 2, 4. Maybe not in the same order they were in before, but that doesn't matter. So I will then recursively sort X. X is an array of length 0. 0 is less than 1, so there's nothing to do when you recursively sort X. But there is some work to do when you recursively sort Y. So then we would compare 3 to everything. I can do that next step. After you do that, you would say in the recursive sort, 3 is the first element of the array you're sorting. And so it ends up here. Here's your X. All the things smaller than 3, there's only one of them. And the rest is bigger than 3. So that's 5, 7, 4. There we go. Okay. All right. Then you recursively sort that and so on. Does anybody see a potential problem here? Anybody see where things can go really badly for quicksort, where quicksort is maybe not so quick? Yeah, so we saw it here. Even in this example, we started with A, and we did all those comparisons to A1, and actually there was nothing in X, and we were stuck with a problem of sorting y, and y still has all of the elements except for one of them. So that's a lot of work. n-1 comparisons just to get rid of one element and then have to recurse on the remaining n-1. That's a lot. In fact, quicksort looks like it could be not so quick at all. And the worst thing about it is it looks like it might be really slow on something that should be really easy. In particular, if the array is already sorted, then when I take the first element and compare it to everything, nothing happens. The first element is there. Everything is, there's nothing smaller than it. Everything is bigger than it. We did n-1 comparisons to get from there to there. And you can say, oh yes, but it's already sorted. But we don't know that yet because we only compared things to 1. We don't know that this is sorted yet because we've never looked at any two numbers here and compared them. We've only compared them to 1, and all that we know is all these numbers are bigger than 1. So then this becomes the y that gets recursed on. It has n-1 elements in it, and exactly the same thing happens again. We recurse on it. Nothing changes. Now this y has n-1 elements in it. We take the first one and we compare it to the n-2 remaining elements. So that means to get from there to there, we're going to do n-2 comparisons. And at the next stage, we're going to do n-3 comparisons. And how long does this go on for? And then n-4, n-5. How long does this go on for? Well, at the very end, we will have an array that has the two largest values in it. We will do one comparison. And then finally only have to recurse on this thing. And it's only then that we're done. Okay. So in the first step of recursion, we do n-1 comparisons just to peel off one element. Then we do n-2 comparisons to peel off an element, then n-3. And we keep counting down like this until we get down to 1. Okay. So that means that the number of comparisons done by quicksort on a sorted array is 1. We can count backwards. It starts at 1. Before that, there was an array of length 3. We had to do 2 comparisons, plus 2, plus 3, plus 4, and so on. And all the way up here, we had to do n-1 comparisons. Now, does anybody know what this adds up to? Someone says n times n plus 1 over 2. That's the correct answer for a different question. If we added this sum all the way up to n, it would be n times n plus 1 over 2. but we're only adding up to n minus 1. So it's actually n times n minus 1 over 2. Or if you like, that's n squared divided by 2 minus n divided by 2. Okay. Now, is that quick? Does that qualify as quick? Why am I counting comparisons? Well, just because it's a concrete thing to count, and pretty much everything, every bit of work that we do is somehow related to comparisons. And certainly, if the comparisons already take a lot of time, then the whole algorithm is going to be slow. So let's see what this looks like. Just take a data point here. If n is 1,000,000, so an array of length 1,000,000 is not very big by modern standards. That's 1,000,000 data items is not a lot of data. That's I don't even know. That's like a small, like a really small event stream for a really small online vendor might get 1,000,000 pieces of click or move information in a day or a week. Amazon gets many more than that in an hour. So if you had to sort those things, and this is the algorithm you're using, or you didn't realize that they were already sorted and you called quicksort to sort them, then this is the number of comparisons it's going to do. And that number for n is 1,000,000, then n times n minus 1 over 2 is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's the number of comparisons that are going to get performed. Now, okay, looks like a big number, but what are we talking about in sort of real time? Computers are fast. Well, computers run at speeds that are measured in gigahertz. So a gigahertz is about 1 billion cycles per second. So a rule of thumb, and the number of gigahertz is not huge yet, right? It's maybe they get up to 5 gigahertz on an overclocked processor, and comparisons probably take more than one cycle in any case. But a good rule of thumb is a modern computer can do 1 billion operations per second. Well, still, that's almost 1 billion there, right? 1 billion has 9 zeros in it. So this is going to be about 999 seconds. And to sort 1 million items, that's a really long time to wait. Okay. 1 million items you should be able to sort much faster than this. All right, and I see in the discussion some of you have said, well, you're just focusing on the worst case here, but on average, it's probably better. That's true. And in fact, that's something that we'll prove. But what's really worrisome about this example is it's not something that's completely unlikely to happen, right? Somebody gives you a data stream, a stream of data. Maybe it's actually time-stamped events. And you didn't realize that they gave it to you already in order, sorted order by time. So you called quicksort so that you could get it in the things sorted by time. And then suddenly quicksort takes 999 seconds to run. And you just wanted to do a quick analysis of this thing. So yes, this is a worst case example, but it's not an unlikely one. Sorted data shows up naturally all the time. So here's what we will study later in this course. With a very small change to quicksort, you can reduce this. So instead of number of comparisons being n times n minus 1 over 2, you can reduce it to 2n times the natural logarithm of n, which is about 1.38 n times the binary logarithm of n. That may or may not mean something to you, but for n equals 1,000,000, this is approximately 27,631,000. Okay, so it drops from about 999 billion to 27.5 million. And if we use our rule of thumb that you can do 1 billion operations per second, this is much less than 1 billion, right? In fact, we don't get to 1 billion until we have 9 digits. So that suggests that this is about 0.027 seconds. So with that small change, you can get this time to drop from 999 seconds to 0.027. So something that you wouldn't notice, the blink of an eye, literally, versus something that you're waiting a good amount of time for, a good, good chunk of time. Okay. And what is the change? The change is trivial. Instead of picking A1, pick a random number between 1 and n, so call that number I, and partition everything with respect to AI instead of always to A1. And then what happens is you are less likely to get this scenario where the thing that you picked happened to be the smallest element and got shoved in the front, and you're more likely, in particular, even half the time, the thing that you pick ends up landing somewhere in the middle half, which is already pretty good. Because if it lands in the middle half, then you get a quarter of the elements at least in X, and you get a quarter of the elements at least in Y, and you don't get this insane thing that runs away. We're not ready to prove that yet. That's going to take some tools from probability, but by the end of this course, we'll be able to prove actually this very sharp result here that tells us that the average running time of randomized quicksort. Okay. All right. And maybe then a good place to finish off today is with a little puzzle. Of course, you can always just look up the answer in the book. So I give you S. It's a set. It has 5 things in it. Maybe the integer is 1, 2, 3, 4, 5. How many subsets S1 through Sk of S can we make so that for any I not equal to j, Si is not a subset of Sj, and Sj is not a subset of Si. For example, I could make singleton sets. So this is my set S1, S2, S3, S4, and S5. So in this case, in this example, I can make 5 different subsets of S, and you can check that none of these is a subset of the other, because actually they're actually completely disjoint. There's nothing in S1 that's also in S3, but in particular, S1 is not contained. It's not a subset of S3, nor is S3 a subset of S1. But you can cook up, more interesting examples. Maybe you take 1, and you take 2, 3, maybe also 3, 4, 4, 5. I don't know, maybe 5, 2, and maybe we'll stop there. 1, 2, 3, 4, 5. Maybe one more just to show that 5 is not the best you can do. Let's say 5, 3. In this case, you get 1, 2, 3, 4, 5, 6 sets, and if you check them all carefully, you'll see that none of these sets is a subset of the other ones. Can you do more than 6? And in particular, what's the maximum number of these subsets that you can make that have this property? And if you solve it for 5 elements, then try it for 6 elements, 7 elements, 50 elements, 1,000 elements. Later we'll see how to prove how to get the exact answer for this problem. So a construction that gets exactly the maximum number of sets, and we'll prove that it's the right answer. Okay, so that's a good place to leave it for today. I'll finish by asking if anybody has any questions. Someone pointed out that indeed, I forgot to divide by 2 here. This is just n times n minus 1. So divide by 2, so it's about 450 seconds. Actually, more than that, 400 and whatever, 999 divided by 2 seconds. Good catch. How did I end up with 2 n ln n? This is the theorem that we'll prove later in the course. It's not at all obvious from anything that I've said already. So the record so far is 10 different sets for S. So see if you can beat that, but don't spend a lot of time. All right. So goodbye, everyone. I will see you next class, which is Monday. Thanks.